Hi, it's Sergey from Replica.io, an open source project set on making a breakthrough in designing and implementing distributed protocols for the future of decentralized computing. This talk is about frameworks for implementing distributed protocols. It's a companion video to the blog post of the same title. You'll find a link to the post in the description of this video. After having explored a bunch of real-world code bases implementing distributed protocols such as consensus without using any framework, I wanted to learn from prior attempts to develop such a framework and hopefully discover some interesting techniques or ideas that would be useful for developing Replica.io. So I explored 7 frameworks based on different programming languages. I looked into their documentation, examples, and also implementation to see how they model the system and structure protocol implementations, what notation they use to specify and implement protocols, how they approach the issues of communication, concurrency, and composition of components, and what they offer to ensure correctness of protocols and their implementations. Here is the list of the frameworks that I explored. Mir based on Go, Atlas based on Rust, Babel based on Java, Distal and psync based on Scala, and Diesel and Verdi based on Coq. It's worth noting that most of them were purely academic efforts and unfortunately seem to be abandoned long ago without finding any practical use. I decided to structure the discussion about distributed protocol frameworks around the following aspects: model, structure, notation, operation, and verification. So the model is how distributed systems and their components are modeled within the frameworks. The structure is how distributed protocol components are structured and composed together. The notation is about what kind of notation is used to specify and implement distributed protocols. Then the operation is about how distributed protocol components are executed and how they interact with each other. And finally, the verification is about verifying distributed protocols and their implementations for correctness. Model is arguably the most important aspect since it has a profound effect not only on the structure and shape of the protocol implementations, but also on the operational aspects and verification. We can talk about modeling at different levels of abstraction, from the high-level model of the system as a whole through modeling of individual nodes within the system down to the models of individual protocols and components within those nodes. The common approach employed by those frameworks is the model of a state transition system, where the system is defined in terms of its state as a snapshot of a system at any particular instant in time, which can only change upon occurring of certain external and internal events. The global state of the system typically consists of the states of individual nodes, their components, and the environment, which usually includes the state of the network with messages in transit, the set of faulty nodes, and this sort of things. State transition, triggered by the events, is defined in terms of a transition function, which is a mapping from the old state of the system and the event causing the transition into the new state of the system. In these frameworks, not only there is no shared state between individual nodes, but also the states of protocol components within those nodes are disjoint. So the protocol components interact following the message passing approach, that is only by exchanging messages between each other. The sending and receiving of messages is modeled as events modifying the system state, and typically updating the set of messages in transit. For example, in Diesel, the system state includes the so-called message soup, which models the current state and the history of the network. In Diesel's abstract model, messages are never removed from the message soup. They are only marked either as active or consumed. Node and network failures are modeled as a kind of special events, such as dropping or duplicating messages in the network, or disabling the normal event handling in faulty nodes, or partially or fully resetting the state of the node. It's worth noting that some of the framework they only consider crash faults, leaving the Byzantine faults for future work. Most of the framework don't seem to clearly model the timing assumptions, so they can be considered asynchronous. Though psync takes a different approach by employing the herd-of model based on communication closed rounds. This approach gives an illusion of synchrony on top of partial synchrony of the actual network. The protocol execution proceeds in explicit rounds with alternating communication and state transition. Network and node faults are unified in this model, and the network assumptions are expressed in terms of the herd of sets. A herd of set is a set of peer nodes that the current node could receive a message from during the communication round. Most of the frameworks model communication between nodes in a rather simplistic way as fire and forget message delivery, where messages can be reordered or dropped by the network abstraction. Though Babel and Verdi approach this differently. In Verdi, protocols are first specified, implemented, and verified in a idealistic, reliable network semantics, and then those implementations can be translated into more realistic, weaker fault models using verified system transformers provided by the framework. Babel introduces the notion of a communication channel abstraction, which allows working directly in a stronger communication model. Communication channels in Babel basically represent communication mechanisms with different properties and guarantees. Individual components within the nodes are normally modeled as sequential, event-driven state machines that interact with each other via reliable message passing. The message passing, in most cases, follows either the one-to-one, one-way, or request-response patterns, though some frameworks also support a one-to-many notifications between components. Some frameworks, like Verdi, explicitly distinguish from the events that are external to the protocol, like client requests, and the internal events, like exchanging messages between components within the system, in order to overcome some limitations of the strict state separation between protocol components. Diesel allows coupling protocols via a special inter-protocol behavior dependencies called sandhooks that provide restricted logical access to other protocol state. It also supports generic composition of protocol components, so it doesn't strictly follow the message passing approach. Diesel also provides a mechanism for establishing stronger properties for protocols and their combinations by strengthening them with additional inductive invariants. So what I observed is that the underlying system model in all of the explored frameworks is largely the same. It's a state transition system where components are sequential, event-driven state machines with disjoint state that interact via message passing. It's remarkably similar to what we can find in the usual real-world implementations of distributed protocols. I would argue that this approach directs the focus more to the operational aspects of the system rather than functional and logical aspects of the distributed protocols. This can cause fragmentation of the protocol logic and code and make the implementation of the protocols more complicated. Adopting basically the same kind of the underlying system model is perhaps one of the reasons why none of the frameworks seem to have made a real breakthrough in designing and implementing distributed protocols. In all of the explored frameworks, there is some kind of runtime or shim that hides the low-level concerns from the high-level protocol implementations. In most frameworks, the runtime is responsible for coordinating execution and interaction of the protocol components. Some frameworks also provide dedicated interfaces for communicating over the network and setting timers as part of the runtime. In most cases, protocol components within the same node can interact with each other by sending some kind of internal messages with no explicit connection required. Though in contrast, Atlas requires that the interaction of the protocol components with the rest of the systems is explicitly orchestrated. Diesel instead supports composition of protocol components expressed as effectful functional programs. It also allows loosely coupling protocol components with inter-protocol behavior dependencies called sendhooks at the level of the formal specification. The runtime in Mir is only responsible for coordinating execution and interaction of components, so there are special components for handling the communication over the network, working with local timers and performing cryptographic operations. Mir explicitly distinguishes between passive and active components, where the passive components can only produce new events synchronously as a result of processing input events, whereas the active components can generate new events on their own. Some of the frameworks provide means for enhancing protocol components with some additional properties. For example, in Diesel, there is a protocol combinator that allows elaborating protocols by strengthening them with some additional inductive invariants. In Verdi, there are verified system transformers that allow transforming protocol implementations from idealistic, reliable network semantics into more realistic, weaker network semantics. In psync, there is a Byzantine round wrapper that takes care of updating the progress conditions and synchronizing in the Byzantine setting. There are two main approaches to structure the interaction of the distributed protocols with the rest of the application. One is by sending and receiving messages, same as the protocol component interact with each other. The other approach is to have dedicated interfaces with callable methods or special input-output events. To trigger side effects from the protocol components, such as sending a message or setting a timer, some frameworks supply the protocol components with dedicated handles. In other frameworks, side effects only happen after returning control back to the runtime, either through the return value or using a monadic structure. Protocol components commonly consist of the component's internal state and the protocol logic, structured as event handlers or state transition functions that are triggered by the runtime upon certain events or conditions and that modify the component's internal state. In Distal and Diesel, those handlers or transitions can be augmented with some guarding conditions that must hold in order to trigger the action. The round-based model of psync imposes a particular structure of components. Protocol components in psync must specify a sequence of protocol rounds, where each round has the methods for first initializing the round, then sending the messages at the beginning of the round, then processing messages as they are received during the round, and finally updating the internal state at the end of the round. Psync and Diesel explicitly separate the protocol specification from its implementation, so that the specification is used to formally verify the implementation. Protocol specifications in Psync consist of the desired protocol properties and safety and liveness predicates or assumptions. In order to aid automated verification, the specification should also include the round and phase invariants. Psync can automatically derive the transition relations from the protocol implementation, although this imposes certain limitations on the code. Protocol specifications in Diesel are defined in terms of the state space coherence predicates and send and receive transitions. The configuration of the protocol components within nodes, as well as their internal structure, can be made more static or dynamic. For example, in Babel, the protocol components and their callbacks are registered within the runtime fully dynamically. The top-level components in Mir are rather static because they cannot be changed after initialization. Therefore, Mir provides a special component, the factory model, that allows creating subcomponents dynamically. It's worth noting that high flexibility at runtime can make the formal verification hard. Therefore, the frameworks that are focused on formal verification, such as Psync, Diesel, and Verdi, they tend to be static. Overall, the abstract model adopted by the framework, be it the generic state transition system with message passing or the Herdov model based on communication closed rounds, largely determines the way the protocol specifications and implementations are structured within the framework. The framework's features, like formal verification, can also add further restrictions, like restricting the flexibility of the runtime in terms of the configuration and internal structure of the protocol components. In terms of notation, the export frameworks rely on the general-purpose programming language they are based on as a primary way to express protocol implementations. In order to enhance ergonomics and expressiveness, most of the frameworks also introduce some notational extensions, such as elements of an embedded domain-specific language. Using a regular general-purpose language allows taking the advantage of the comprehensive language features such as the type system, polymorphism, inheritance, metaprogramming, and so on. On the other hand, implementing protocols in regular code can also have some undesirable effects, such as non-determinism, for example, when iterating over built-in unordered data structures, which can be problematic for reproducible simulation-based testing. Because of that, for example, Mir provides some utility functions to be used instead of the usual idiomatic code to avoid this kind of non-determinism. The rich expressiveness of the general-purpose languages can also make it difficult to perform automatic verification. For example, Psync has a rather limited support for generic scalar construct in its automatic derivation of the round transition relations. In most cases, the notational extensions are introduced there to make the code more declarative and concise. One of the main targets for such enhancements is to provide a convenient way to express the protocol implementations similar to the typical event-oriented pseudocode as found in the literature on distributed systems. A good example of that are the rules in Distal, which allow to express event predicates in a declarative style, both for simple events triggered by single messages, as well as for composite events triggered by collections of messages. The other reasons to introduce notational extensions is to express certain actions performed by the protocol logic and overcome the host language limitations. For example, distall provides a special notation for actions to send messages, discard messages, and schedule actions in future. Diesel has extensions for effectful commands, monadic composition, and general recursion. Diesel also provides the transition wrappers for sending and receiving messages that lift the low-level operations to the well-typed program primitives. Verdi has a monad for sending messages, emitting events, and manipulating the current state, as well as a convenience notation for various monadic bindings. Finally, notational enhancements can also be useful for expressing the protocol properties, assumptions, and invariants, as well as the related annotations in the protocol implementation. For example, in psync, there is a DSL for expressing properties, predicates, and invariants, the key element of which is the domain primitive representing sets of values with the operations for universal and existential quantification, as well as the set comprehension. Diesel has a special notation for expressing the higher order Hoare types of program fragments. Many elements of DSLs can be implemented using only the common programming language techniques such as polymorphism, inheritance, composition, higher order functions, and type system features. For example, most of the distal's DSL is implemented just as ordinary methods and convenience aliases. Though these common techniques have certain limitations, and sometimes more advanced techniques such as metaprogramming or macros and code generation may be required. For example, the key elements of the distal DSL and psync's derivation of transition relations are implemented as a macro. Code generation in Mir can significantly reduce the handwritten boilerplate. Diesel and Verdi also take advantage of Cox syntax extension features. Clear and convenient notation is absolutely crucial for ergonomics and expressiveness of the protocol implementations. So building upon the ordinary code and using the common programming language techniques in a clever way should be the preferred approach for achieving the notational expressiveness. More advanced techniques such as metaprogramming and code generation can help overcoming certain limitations or further improve the notation, but they can also make the framework more complicated, therefore they should be employed judiciously. In terms of operation, the core part in most of the frameworks is some kind of runtime or engine that orchestrates the execution and interaction of the protocol components. For concurrent execution of protocol components, the runtimes mostly rely on the conventional concurrency mechanisms that are used in the framework's language ecosystem, such as Go routines in Go or execution pools in Java and Scala. It's worth noting that in terms of concurrency, Atlas is based directly on the native operating system threads rather than an asynchronous Rust runtime like Tokyo, presumably due to performance reasons. There are two main approaches to implement the message passing interaction between the protocol components and with the network layer. One is by using some kind of central event dispatching loop, which is the case in Mir, and another approach is to use an explicit channels like in Atlas. Since different components can operate asynchronously with respect to each other, there is often some kind of event queue or buffer that is placed between the components in order to accommodate for the asynchrony. This naturally raises an issue of preventing unbounded growth of those queues or buffers. For example, Mir addresses this problem by blocking the influx of all external events when an internal queue is filled beyond a certain threshold. Atlas, on the other hand, relies on the built-in flow control provided by the bounded buffer channels. In general, garbage collection is an important issue in distributed protocol implementations. Sometimes it can be performed automatically. For example, in pissing, the received message sets are automatically discarded on the round transitions. In some cases, however, it requires explicit control. For example, in distal, the buffered messages must be discarded explicitly in order to prevent unbounded growth of message buffer and slowing down the evaluation of rules. There is an interesting pattern in Mir whereby disposable pieces of state are assigned numerical retention indexes that can be used to remove the irrelevant pieces of state whose retention indexes are below a certain value. As already mentioned, the communication between nodes is implemented in most of the frameworks in a rather simplistic way with best effort message delivery and following the fire and forget communication style. Babel is a notable exception since it introduces the communication channel abstraction, where different channel types can provide different properties and guarantees. For example, more reliable message delivery, multiplexing connections, or phi accrual failure detection. So, orchestrating execution and coordinating interaction of protocol components often require some kind of runtime to be provided by the framework. The runtime should take care of asynchrony, garbage collection, communication, and coordination within the node. It should also prevent unbounded growth of the internal state and ensure good performance. Let's finally talk about verification. Not all of the explored frameworks were particularly concerned with verifying correctness of protocols and their implementations. Verification is the primary area of focus in Diesel and Verdi as well as in pacing. It was not a major concern in Mir, though it provides some kind of lightweight verification mechanisms. Mir allows recording, inspecting, modifying, and replaying traces of events, which was primarily meant for debugging, but it can also be used for correctness analysis. Mir comes with a simple discrete event simulation runtime, which can be used for randomized, reproducible testing. Full-fledged formal verification we can find in Diesel and Verdi, which rely on machine-assisted theorem proving, whereas pacing attempts to automate the process. Theorem proving, even when machine-assisted, is a difficult, time-consuming process and requires special expertise. Automated verification is unfortunately, in general, undecidable and can only be achieved with certain restrictions on the system model and the implementation. Formal verification requires formal specification of the assumptions and the required properties. In Diesel, protocol specifications are defined in terms of state space coherence predicates and send-receive transitions. In Verdi, the correct behavior of the protocol is defined in terms of logical predicates over possible traces of events. Formal specifications in psync are stated in terms of protocol properties and safety and liveness predicates or assumptions expressed in a fragment over first-order temporal logic with cardinalities of heard-of sets. The general method of proving protocol correctness in these frameworks is by induction, which requires constructing inductive state invariants. Coming up with a proper state invariance is the greatest difficulty in the verification effort, and it requires special kind of skills. In psync, the simple round-based structure with lockstep semantics allows automated verification, though it still requires stating inductive invariance at the boundaries between the rounds. However, the automated verification problem is decidable with certain constraints. Correctness of protocol implementations in Verdi is proved directly, whereas Diesel takes a different approach. For implementing protocol specifications, Diesel introduces a domain-specific language shallowly embedded in Coq that extends Coq's specification language Galena. Diesel programs and their fragments are assigned types that correspond to the protocol specification in higher order separation style or logic. For message sending and receiving actions, Diesel provides special transition wrappers that lift those low-level operations to the level of well-typed program primitives. Those primitives correspond to the protocol specifications, and therefore the well-typed programs are correct by construction with respect to the protocol specification. In Verdi, once the protocol is specified, implemented, and verified in an idealistic, reliable network semantics, it can be translated into a weaker, more realistic fault models, preserving the protocol properties using the verified system transformers. In Diesel, the generic protocol specifications with their proven invariance can be used in composition. Diesel also provides mechanisms to establish stronger properties of protocols and their combinations by strengthening them with additional inductive invariance. Correctness is very important for critical fault-tolerant protocols, therefore the verification aspect deserves special attention. On one hand, there are lightweight methods that are relatively easy to apply, like randomized reproducible testing with discrete event simulation. On the other hand, there are more reliable, sophisticated formal methods like machine-assisted theorem proving, though they are more expensive and require special skills. Some particularly structured system models may enable automated reasoning, making the formal verification more practical, but they come with additional limitations. So we've talked about the models adopted by the frameworks for implementing distributed protocols, the structure of protocol implementations within those frameworks, the notational enhancements introduced there, the operational aspects, as well as their approaches to verify the correctness of protocols and their implementations within those frameworks. Now let's make some conclusions. Having explored these 7 frameworks for implementing distributed protocols, I found most of the frameworks not sufficiently developed for practical use, though some ideas and techniques employed there were worth exploring. Most of these frameworks were purely academic efforts and seem to have been abandoned after having explored some ideas and published the results. MIR is perhaps the most mature, well-documented and up-to-date among those frameworks. It may be appropriate for academic research to focus on some aspects like unifying and standardizing components, testing and debugging, notational convenience or formal verification, while mostly neglecting the other aspects, but this is certainly not enough for real practical adoption. Moreover, the programming languages most of the framework are based on may be hard to integrate directly into larger code bases written in other languages, or require learning some less commonly used languages like Scala or Coq, which is an additional obstacle for adoption. Most importantly, perhaps, is that all of these frameworks for implementing distributed protocols seem to adopt basically the same model of a state transition system, trying to mimic the event-oriented notation of typical pseudocode found in the literature on distributed systems. This largely impacts how protocol implementations are expressed and structured within those frameworks. I believe if we want to make a real breakthrough in both designing and implementing distributed protocols, which is what the Replica.io project is about, we should first of all be innovative, trying to challenge the status quo and think holistically, taking into account all the relevant aspects. A good start would be trying to rethink the conventional model of a distributed system and the ways of expressing distributed protocols. Having explored a bunch of real-world code bases implementing distributed protocols and a number of frameworks for implementing distributed protocols, now it's a good time to clearly state the problems in designing and implementing distributed protocols to focus on for the rest of the milestone and start gathering ideas on how to approach those problems. Apart from that, there are potentially related concepts, approaches and techniques that are worth looking into as part of the initial state-of-the-art exploration. Once the initial exploration is over, it will be time to come up with the key ideas concerning the core principles of designing and implementing generic components within the framework, which is the goal of the milestone M0.1. Then those rough ideas will be developed into clearly formulated concepts in milestone 0.2. Their feasibility will be verified with actual code in milestone 0.3. Then the prototype, MVP and production versions of the framework will be developed and released in milestones 1, 2 and 3. Though the exploration, ideation and prototyping will also take place at later stages, the milestones simply define the general level of framework's maturity. The framework will be continuously developing, evolving and expanding until it becomes a de facto standard for implementing critical fault-tolerant systems, providing a growing collection of ready-to-use, reliable and efficient distributed replication mechanisms. If you want to learn more about the project, please go and visit its website. There you'll find some links to follow the project and participate. You'll find a link to the website in the description of this video. You can also support the further development of this project by sponsoring it on GitHub. If that does not work for you, please drop an email and we'll find a solution. That's all for now. Thanks for your interest.